Graphing rational functions. So in this lesson, we will be talking about how to sketch a rough graph of rational functions and identify the vertical and horizontal asymptotes. Later on in lessons 2 and 3 of graphing rational functions, we'll talk about slant or oblique asymptotes. Today we'll also learn about holes in graphs, how to identify them, the domain, x and y intercepts, and eventually we'll get to what is the end behavior of rational functions. Here are some rules. In order to identify vertical asymptotes of a graph, we're going to take the denominator, set it equal, and solve. We can find the x-intercepts of a graph by setting the numerator of the rational function equal to 0 and solving. And to find the y-intercepts, we'll input 0 in for x and then solve for y. Horizontal asymptotes are a little bit trickier. We're going to identify the degrees of the function. As a reminder, if you were in class, when I introduced to you rational functions, I explained that a rational function is simply the dividing of two polynomials. So a rational function can be determined by dividing two rational functions. So we are going to identify the degree of the numerator and the denominator. And then by analyzing those values, the degree in the numerator and the denominator, we'll be able to tell if a horizontal asymptote exists and what that value would be. If the degrees in the numerator and the denominator are equal, we can achieve the equation of the horizontal asymptote by taking the ratio of the leading coefficients. That means dividing the leading coefficient in the numerator by the leading coefficient in the denominator. If the degree of the numerator is less than the degree of the denominator, we will always have a horizontal asymptote of y equals 0. And lastly, no horizontal asymptote will exist if the numerator is larger than the degree of the denominator. And in that case, we'll learn in lessons 2 and 3 that a slant or oblique asymptote occurs. Now, one thing to know is that our rational function will never ever cross over or intersect with a vertical asymptote. Occasionally we will see our function actually intersect or cross a horizontal asymptote, and when that occurs, it will happen in the middle of the graph, not on the far ends of the graph. Let's get started. How can we identify the horizontal asymptote? We're going to come right back to these rules, so let me go ahead and erase that. So let's first look at the degrees of the numerator and denominator. Notice there's no x on top in this first one. So this is the same as x to the 0 over, make sure that looks like a 0, over x squared minus 9. And I'm focusing on those degrees. In this case, I can see the degree in the numerator is less than the degree in the denominator. 0 is less than 2. So I'm going to come back to the rules, and we can see when the degree in the numerator is we don't want larger. When the degree in the numerator is less than the degree in the denominator, we will always have a horizontal asymptote of y equals 0. This is the horizontal asymptote. Okay, in example number 3, we're going to skip, by the way, and do 2, 4, 6 on the next slide. In example number 3, we have a degree of 2 in the numerator and a degree of 1 in the denominator. So 2 is greater than 1. So in this case, in example number 3, the degree is larger in the numerator. When the degree is larger in the numerator, no horizontal asymptote exists. So coming back here, our horizontal asymptote does not exist for example number 3. Let's look at example number 5. Here we can see a degree 1 and also a degree 1. So 1 equals 1. When the degree in the numerator is equal to the degree in the denominator, we're able to achieve this by identifying the leading coefficients. So the leading coefficient in the numerator is 9, and the leading coefficient in the denominator is 2. It's those values in front of the x to the first in the numerator and the x to the first in the denominator. So we're going to create a ratio of this. Y equals 9 over 2. And that's equivalent to 4.5 if you prefer to write it in decimal form. I would like you to press pause if you're rewatching this video or if you missed class, and I'd like you to attempt 2, 4, and 6, and then come back to the video to watch me go through those 3 examples. Example number 2, I can see we have equivalent degrees. 2 is equal to 2, And so I will apply this rule here. And the rule is if they are equal, that's right here, if they are equal, I'm going to take the ratio of the leading coefficient in the numerator and the denominator. So y equals 6 over 2. The horizontal asymptote is then y equals 3 when we reduce it. Let's look at example number 4. We have a degree of 1 in the numerator and a degree 2 in the denominator. So the numerator is less than the denominator. When the degree in the numerator is larger, nope, I don't have that. When the degree in the numerator is less than the degree in the denominator, we will always have a horizontal asymptote of y equals 0. Our last one, we have a degree 3 and a degree 1. So 3 is greater than 1, and that's going to be that third rule. When the degree in the numerator is larger than the degree in the denominator, our horizontal asymptote will not exist. It's not available. Let's now talk about holes in graphs and vertical asymptotes. And we'll use the technical language when we talk about graphing rational functions in lesson 2 and lesson 3. So right now, the first thing I'm always going to do is I'm going to ask myself, is it possible that I look at example 7 and I can actually move forward with factoring this? Y equals x minus 3 over, now this is equivalent to x minus 3 and x plus 3. So when I look at the numerator and I look at the denominator, notice that the denominator is a product of linear factors. It has to be written as a product in order for us to reduce. So I am able to reduce these. They don't cancel out. They're really going to reduce down to 1. When I rewrite this, I have y equals 1 over x plus 3. This is the reduced form of this original equation. Whenever you can simplify, like I just did here, whenever you can simplify, and whatever you just simplified contains a variable, contains a variable x, then we need to take that amount and set it equal to 0. And that's going to identify where we see a hole in the graph. So I know a hole exists in the graph at x equals 3. A hole exists in the graph. A vertical asymptote can be identified once it's in simplified form by looking at the denominator, and if the denominator contains a variable, we're going to set it equal to 0 and solve. So a vertical asymptote occurs at x equals negative 3. Let's move on right now to example number 9. Let me erase this to provide us with more space. Okay, so I'm looking at number 9, and I can see number 9 is not in factored form. So let's go ahead and factor number 9. I'm asking myself, if this is factorable in the numerator, what two values multiplied to equal negative 2 and combined to equal positive 1? X plus 2 and x minus 1. In the denominator, x plus 3 and x minus 2. Now, it's probably really common for students to look at this top factor and this bottom factor and think, oh, I can simplify those. But x plus 2 is different than x minus 2. So in this case, I'm not able to simplify things. A lot of students, again, want to use the word cancel out. Not canceling out, but we're simplifying. I can't do that. That means there exists no holes in this graph. No holes exist. But now we're going to look at the denominator and set both of these linear factors equal to 0 in order to identify the vertical asymptotes. So I'm going to subtract 3 to both sides. X equals negative 3 and x equals positive 2 are going to be the vertical asymptotes. Moving on to our last example, let's look at number 11. What I commonly see for number 11 is that students are very eager to reduce or simplify the rational function. And so what they often do is they want to cancel out the x's. Remember, we cannot simplify unless something is written as linear products. So when I see this, it really is x subtract 2, that's one quantity, over x plus 2. We can't separate the x plus 2, and we can't separate the x minus 2. So we are unable to reduce anything here. That means there is no holes that exist in this function. Now to identify the vertical asymptote, I'm going to take the quantity x plus 2 and set it equal to 0, and we have a vertical asymptote occurring at x equals negative 2. I'd like you to press pause and please do 8, 10, and 12, and then come back to this video to see if you correctly we're able to identify the holes and vertical asymptotes. All right, problem number 8. Let's start by simplifying. In the numerator, I can factor out an x. In the denominator, I can factor out a 2. And then I realized that the denominator can be rewritten one more time. X squared minus 1 factors into x plus 1 and x minus 1. Now you can see that the numerator and the denominator are both written as a product of linear factors. So let's go ahead and reduce. Notice that the 6 and the 2 can reduce to 3 over 1. And so you may be wondering, does that mean there's going to be a hole because I just reduced? Well, 6 and 2 don't contain a variable. They're just values. They're just numbers. And so for that reason, reducing this, although it's valuable, does not actually show us any hole. But x plus 1 and x plus 1 can be reduced. So this is 3. Remember, these turn into 1s. So 3 times 1 gives me 3 in the numerator in reduced form. 1 times 1, these are multiplying. So 1 times 1 times x subtract 1 is x subtract 1. Now here I was able to reduce the quantity x plus 1 and x plus 1 because it contains a variable. I'll take the x plus 1, set it equal to 0, and I can see that x equals negative 1 will identify a hole in this rational function. How do we identify the vertical asymptotes? In this case, we take our denominator, set it equal to 0, add 1 to both sides, and I get a vertical asymptote of x equals positive 1. Let's look at example number 10. Example number 10, same as example number 8, we're going to start off by reducing this. So I'm going to pull an x out of the numerator, and I'm left with x minus 1. In the denominator, I can pull out an x, and I'm left with x squared minus 1. Now this kind of looks like a combination of previous functions. I recognize that x squared minus 1 factors into x minus 1 and x plus 1. And notice that I now have the product of linear factors. Let's see what we can reduce. So x and x are able to reduce down to 1, but they contain a variable. That means I'm able to share that we have a hole when x equals 0. So I take this quantity and I set it equal to 0. I also, x minus 1 equals 0. I add 1 to both sides. I also have a hole at x equals 1. Now when I reduce these, each of these quantities turns into 1. So when I rewrite this, I have y equals 1 times 1 is 1, and 1 times 1 times x plus 1. So this is what I'm left with after I reduce. Now to find the vertical asymptote, I take the denominator, I set it equal to 0, and I get x equals negative 1. This is going to be my vertical asymptote. Let's look at our final example, example number 12. All right, so many students will look at x squared plus 1 and they'll say, well, doesn't this factor into x plus 1 and x minus 1? That's not the case. It's not a difference of squares. Other students will say, well, does it factor into x plus 1 and x plus 1? No, that's not the case. If we FOILed this out, we'd end up with x squared plus 2x plus 1. And remember that factoring something means it must be equivalent to the original expression. So there's nothing we can do at this time to rewrite the numerator and the denominator. So I am unable to simplify anything. That means there's no holes. I take the denominator, I set it equal to 0, and in this case I add 1 to both sides, and our vertical asymptote for example number 12 is x equals 1. Okay, we're going to come back to these rules, and now we're going to go ahead and proceed, and when we look at this equation, we're going to identify the x-intercept, the y-intercept, the vertical asymptote, and the horizontal asymptote. So when I look at this example, I don't see any x on top. Remember, that's the same as x equals 0. Not having an x is the same as x equals 0. So let's look at the degrees. I'm going to start off with what is the horizontal asymptote. Okay, so the degree in the numerator is 0, and the degree in the denominator is 1. So the numerator is less than the denominator for the degrees. Let's find out. When the degree in the numerator is less than the degree in the denominator, we have y equals 0. Okay, so my horizontal asymptote is y equals 0. I'm going to go ahead and let's see if I can actually highlight this. And I'm going to highlight this across. Okay, I'm going to come back up here, erase what I have to make it a little bit easier to read. And now let's go ahead and let's identify the vertical asymptotes. So our vertical asymptote is achieved by first looking at the function and asking ourselves, can we simplify? Because if we could factor something and simplify, it's possible we'd identify a hole in the graph. Can't simplify anything here, so I'm going to take the denominator and I'm going to set it equal to 0. And we're not just going to get a value of 2 of x equals 2. It's an equation x equals 2. That is the vertical asymptote. I'm going to take a different color and a highlighter here off to the side. And I'm going to go to x equals 2 and draw that line down. So I've identified the vertical asymptote and I've identified the horizontal asymptote. Now let's look at what is the x-intercept and the y-intercept. So to achieve the x-intercept, I gave you a helpful hint during the lesson today. I said, what we do, here's the long way of doing it. When we find the x-intercept, we always have y equal to 0. So let's do that. I just set y equal to 0. And we can always write 0 over 1, right? We can write 1 over any value. Now if I was going to solve this, I'd cross multiply. Well, 0 times x minus 2, 0 times anything is 0, and 1 times 3 is 3. Well, 0 does not equal 3. That's not a true math statement. That means there is no x-intercepts for this particular example. Also, remember that the shortcut I explained in class moving forward is we can always set 0 equal to whatever the numerator is. So in the future, we can always set 0 equal to the numerator. Let's now determine the y-intercept. To determine the y-intercept, we're going to take x and set it equal to 0. So I'm going to come up here and write y equals 3 over 0 subtract 2. That means y equals 3 over negative 2. So y is equivalent to negative 1.5 or negative 3 halves. So negative 1.5 would be right here. Now in order to do a rough graph of this, I want at least 2 points to the left of each vertical asymptote and 2 points to the right of each vertical asymptote. So let me go ahead, erase all of this to get a prettier picture. And I'm going to make a little graph here. So here's my t-chart. I already have 1 point to the left. I know 0 is equivalent to negative 3 halves or negative 1.5. I only need one other point. I want to make my life easy. Let's choose 1. So I'm going to substitute in 1. I'm going to do the math right here and then I'll get an answer. So I have 3 divided by, and now I'm going to substitute 1 in for x. 1 minus 2. Well, that would be 3 over 1 minus 2 is negative 1. Okay, so when I substitute in 1, my input is 1 and my output is negative 3. Input is 1, output is negative 3. And in class we talked about how as we move to the left and the right, our function will get closer and closer to the asymptotes. Now I need 2 values to the right of the vertical asymptote. Well, let's make this easy. Let's do 3 and 4. Start with 3 and then we'll do 4. So I'm substituting in 3 for the x. 3 divided by 3 minus 2. Okay, well that's 3. 3 minus 2 is 1. I get an answer of 3. When I input in 3, I get an output of 3. Let's try 4. I input 4 in for x. That leaves me with 3 over 2. Well, that's the same as 1.5. So I move over 4 and up 1.5. Let's see, here's 1, 1.5. And now I have a pretty accurate rough graph. Let's move on to example number 2. Example number 2. Example number 2, remember our first step, if we can, we want to rewrite this in factored form. So let's factor to 2. I'm left with x plus 3 over x plus 1. Okay, so I'm not able to simplify anything. Now, whether you start with identifying the horizontal or the vertical asymptote is up to you. You just want to be consistent with what you're doing. I'm going to start with the horizontal asymptote. So I'm looking at the degree in the numerator and the degree in the denominator, and they both are a degree of 1. As a reminder, when the degree in the numerator is equivalent to the degree in the denominator, they're equal, we are going to identify the leading coefficients and create a ratio. So I know the horizontal asymptote is always the variable y. It's creating an equation with y equals, and I'm going to take 2 and divide it by the 1. 2 divided by 1. Well, 2 divided by 1 is simply 2. So off to the side, taking that highlighter, I'm going to y equals 2. It cuts through the y-axis. And now I'm going to come up here, just for the purpose of keeping this neat, and erase. There is no holes in this particular graph because I can't cancel anything out up here. I can't, I used the wrong term, cancel out, I can't simplify anything. All right, let's move on to identifying then what is the vertical asymptote. I'm always going to take the denominator and I'm going to set it equal to 0 and I'm going to solve. So x equals -1 is going to be our vertical asymptote. Let's move forward with identifying what is the x and the y. What is the x and the y intercepts? So I'm going to start with what is the x-intercept. Now remember, I shared with you a helpful hint. Here's the shortcut. We always take 0 and we set it equal to the numerator. Whether you use 2x plus 6 or you write down 2 times the quantity x plus 3 is totally up to you. So in this case, I'm dividing by 2. 0 equals x plus 3, subtracting 3, and I get x equals -3. So I'm going to come off the graph and I'm going to find -3. That is my x-intercept. Let's identify the y-intercept. So for the y-intercept, I'm going to replace all of the x's with 0. I personally think it's easier to use this version of the equation, but you can use the original. So 2 times 0 plus 3 over 0 plus 1. That would be 2 times 3 over 1, which is 6 over 1, which is simply 6. So I'm going to go way up here. Now, in order for us to accurately graph or sketch a rough graph of this rational function, we need to have 2 points to the left and the right of every vertical asymptote. So I'm going to move forward in making my little chart here. I already have 1 point to the left. Notice I have -3 goes with 0, and I'm going to come down here and I have 0 goes with 6. So I need one more point to the left of the vertical asymptote. I'm going to plug in -2. Let's do it in a different color so it stands out. So I'm going to plug in -2. Let's do the work here. So I have 2 times, so I'm going to substitute 2 in for x and 2 in for x in the denominator. That gives me 2 times 5 over 2 plus 1 is 3. So I end up with 10/3. Okay, well 10/3, if we use a calculator, is approximately 3 1/3. I just want to make sure. Oh, I made a mistake. I didn't plug in. I plugged in 2 and it was supposed to be a -2. So let me come back here and switch this up here. Give me 1 second to switch this up. So 2 times -2 plus 3 over -2 plus 1. 2 times -2 plus 3 is 1, and -2 plus 1 is -1. When I simplify this, I end up with -2. So -2 belongs to -2. So I'm going to go over to -2 and down to -2. So we can already see on the left side of this graph, we're able to get an idea of what this looks like. And remember, as it approaches both the horizontal and the vertical asymptote, it's going to start to hug those lines. It never actually intersects or touches them, but it's going to get closer and closer to them. Now let's choose one more value to the right of the vertical asymptote. Notice I already have a value when x equals 0. Okay, one more. Let's plug in 1. It seems like an easy value to plug in here. So I have 2 times 1 plus 3 over 1 plus 1. 2 times 4 over 2, that's 8 over 2, which is 4. So I'm going to go over 1 and up 4, and again, it just provides me a more accurate view of this rough sketch of the rational function. All right, let's move on now to our third and final example here. Let's go ahead and look at this one. All right, is it possible for me to go ahead and factor? Let's try. Do I know two values that multiply to equal -6 and combine to give us -1? I do. X subtract 3 and x plus 2. Now that's going to be helpful in identifying the vertical asymptotes, but it's not going to, it looks like it's not going to provide me with any insight to hole. So there will be no hole in this particular graph. Let's go with the horizontal asymptote. Sorry. Let's go with the horizontal asymptote. The degree in the numerator is 1. The degree in the denominator is 2. So the numerator is less than the denominator. When the numerator is less than the denominator, we have a horizontal asymptote at y equals 1. Oh, y equals 0. Excuse me. There we go. I really wanted to stay the same color. There we go. Okay, let's move on right now to the vertical asymptotes. So we already know that no holes exist because we're not able to reduce anything. So I'm going to take each one of the denominators, each one of the factors of the denominator, and I'm going to set it equal to 0, and I'm going to solve. So adding 3 to the opposite side gives me one vertical asymptote of 3, and it gives me another vertical asymptote of x equals -2. So this one's going to look a little bit different than our previous two examples. Okay, I am going to come over now to +3 and to -2. And notice I have 3 regions on the top and 3 regions on the bottom. Remember, everything we're graphing out right now is a rational function. So I would have to be able to apply the vertical line test and it would work. So when we start to graph this, I will demonstrate that. Let's go ahead and erase this. And let's jump into what are the intercepts of this function. So let's start with the x-intercept. The x-intercept, we learned that there's a shortcut. We can take 0 and set it equal to the numerator. So 0 equals the numerator is just 0. So I know that, look at this, not only is that the x-intercept, it's also the y-intercept. As a review from your freshman year, remember that all of your functions, unless there's a restriction on the domain, all of your functions will have at most one y-intercept. There would not be a y-intercept if somehow we restricted the domains, but otherwise there's going to be a y-intercept. We can see it here. And you can have multiple x-intercepts. In this case, we only have one. All right, well, what do we do now? Well, remember, we're going to choose 2 points to the left and 2 points to the right of every vertical asymptote. So I'm going to get started here. I'm going to start with going off to the far left. So I know I can't choose -2 because that's the vertical asymptote, but let's choose -3 and let's choose -4. So I'm going to plug it in here. I have -3 divided by, and then -3 minus 3, and -3 plus 2. That gives me -3 over -6 times -1. Okay. And that gives me -3 over +6. That's the same as -1/2 or -0.5. So I'm going to go over to -3 and up to 0.5. So here would be, oh, it's negative. So here would be -1 over to -3, and here would be -0.5. Whoops, that's the ordered pair, -3, if I can do it there. There's -3 and -0.5. All right, let's go ahead and let's figure out now what would be the corresponding or the output value when we input in -4. -4, -4 minus 3, and -4, ooh, that's ugly, -4 plus 2. -4, -7, and -2. So this would be -4 over 14. So I need to see what is -4 over 14. I know that reduces down to -2/7, but what is that approximately equal to? So I'm going to grab a calculator really quick. That's approximately, it's really close to being at 0.3. So just a little under 1/3. So I'm going to graph, this is really close. This is really close. It's actually -0.28, and it's irrational number. It goes on and on. So I'm going to go over to -4, and remember this would be at 1/2, so I need to be a little bit above that. Oh, it's hard to see that, right above there. And then we have those 2 points. We can see it's going this way. It's getting closer and closer to the asymptote. As a quick reminder, at the beginning of this video, I shared, remember that our function will never cross, intersect, touch a vertical asymptote. Occasionally, it will intersect or cross a horizontal asymptote, and when that occurs, it will be in the middle of the graph. And here's a perfect example. See how it crosses, that purple dot crosses the horizontal asymptote, but it does it in the middle of the graph. It doesn't do it at the far ends of the graph. All right, so I got the one part done now. I'm going to erase this and we're going to, oh no, let's come back here. I'm going to erase, oh goodness sakes. There we go. I'm going to now choose the middle section. So I already know what 0 is, and it's possible that I may have to choose more than one input value just to get an idea of what this looks like, especially because it looks so different than the other two examples. Oh gosh, well, let's look here. Looks like I unintentionally erased something here. So we knew that there was also, here is, I erased the wrong thing, didn't I? All right, let's look at this middle section. So I already know that 0 belongs to 0, right? But I need to know, what is that middle section going to look like? So I'm going to choose a number like -1. And I'm also going to choose a number like +1. And if I need to, if I still don't know, I'll choose 2. So I'm going to start by plugging these in and see what I get. So right here is where I'm going to plug it in. I'm inputting -1 divided by, well, when I substitute this in, -1 minus 3 is -4, and -1 plus 2 is +1. So I have -1 divided by -4. Okay, that's +1/4. I can graph that. So I'm going to go -1 to the left and up 1/4. That's going to be like right here. All right, so next up is I'm going to now work with 1. So now I'm going to substitute in a +1. So 1 divided by 1 minus 3 is -2. 1 plus 2 is 3. And I end up with 1 over -6. So when I go over 1, I'm going to go down 1/6. That's what, right there. Still, I don't have a great idea what this looks like, so I'm going to actually go ahead and plug in 2. So I have 2 over 2 minus 3 is -1. 2 plus 2 is 4. And this is going to equate to 2 over -4. Okay, that's going to be -1/2, which is right here. All right, that's enough information for me to see. I got to go through those points. So through this point, through this point, and through this point. Remember that as you get closer and closer to the vertical and horizontal asymptotes, it's going to hug those lines. We got 2 points left to do. I'm going to try 4 and I'm going to try 5. I want 2 points to the left and the right at a minimum of every vertical asymptote. Let me erase this. So I'm going to plug in 4 and I'm going to plug in 5. All right, let's start with 4. So 4 divided by 4 minus 3 is 1, and 4 plus 2 is 6. Okay, so 4 over 6, well, I know that's the same as 2/3. 2/3, or 0.6 repeating. So go over 4, I know here's 1, here's a half, so somewhere right about there. Remember, this is a rough sketch, but you want to get in the general area, right about there. Now let's plug in 5. I have 5 divided by 5 minus 3 is 2. 5 plus 2 is 7. So I have 5 over 14. Well, I know 5 over 15 is 1/3. So this is really close to 1/3. In fact, if I use a calculator really quick, it's 0.35 approximately. Okay, so I'm going to go over to 5, and I know this is going to be a half, and this is 1. So a little bit less than a half. And that allows me to get the general idea of what this looks like.